For decades, our clearest views of the universe came from orbit, Hubble, James Webb, Chandra, instruments that escaped Earth's blurring atmosphere entirely. That assumption just broke. A telescope still rooted to the ground, still fighting through our turbulent air, has produced images so vast and so sharp that veteran scientists reportedly went silent when they first saw them. On its very first night of operation, the Vera Rubin Observatory opened its eye to the sky, and what came back was staggering. A camera roughly the size of a small car, capturing 3.2 billion pixels in a single frame wide enough to swallow 40 full moons at once. The data pouring out is so immense that researchers will spend years processing a single night's work. Yet even its earliest test images had already caught colliding galaxies, infant stars, tens of thousands of ancient star clusters, and more new asteroids in one night than global observatories once found in weeks combined. This is a machine astronomers have waited a generation for, one capable of watching the entire sky change in real time. Here's what the Rubin Observatory has just revealed, and why its debut images sent shockwaves through the scientific world. This observatory didn't simply appear overnight. It took more than 2 decades of proposals, funding battles, and political negotiation before it was finally assembled piece by piece at 2,682 meters above sea level on Cerro Pachón in Chile's Coquimbo region. The site was chosen deliberately. The nearby Atacama Desert is one of the driest places on Earth. Rain almost never falls, clouds are rare, and light pollution is essentially non-existent. On a clear night there, the atmosphere is calm and transparent enough that ground-based observation begins to approach what you get from space. The facility is named after Vera Rubin, the astronomer whose 1960s research helped prove one of physics' biggest mysteries. Studying nearly 60 galaxies, she found stars at their outer edges spinning far too fast for the visible matter to hold them together. Yet the galaxies stayed intact. Something invisible was providing the extra gravity. Rubin's work became the strongest early evidence for dark matter. The project that would eventually bear her name started as rough sketches in the early 1990s, originally called the Dark Matter Telescope. By 2001, it had grown into the Large Synoptic Survey Telescope, with a far bigger goal: photograph the entire sky repeatedly and catalog everything from asteroids to exploding stars to the deepest structure of the cosmos. Between 2001 and 2010, funding arrived from the National Science Foundation, the Department of Energy, and private donors, including Charles Simonyi and Bill Gates, whose combined gifts reached roughly $30 million. At the heart of the observatory sits the Simonyi Survey Telescope, unusual for using 3 mirrors instead of the typical 2, a configuration that delivers sharp, undistorted images across a 3.5-degree field of view. Every exposure covers 9.6 square degrees of sky, more than 40 times the area of a full moon, something no other large telescope on Earth can match. Its 8.4-meter primary mirror feeds the LSSD camera, the largest digital camera ever built for astronomy. Nearly 2,800 kilograms, about 3 meters long, packed with 89 sensors calibrated so precisely that a star at the edge of the frame looks as sharp as one at the center. It records across 6 wavelength bands, from ultraviolet through visible light into the near-infrared, and one of its lenses is the largest ever made for an astronomical instrument. A robotic filter system swaps between bands in seconds, letting the telescope gather multiple data types from the same patch of sky in one night. Combined, this gives it a light gathering and field of view rating more than triple that of any previous wide-field telescope. The camera was built at SLAC National Accelerator Laboratory. The telescope and site are run by NSF's NIR lab. When the first images finally dropped, watch parties spread across 6 continents, with viewers in 28 countries tuning in live. That reveal came at a public event in mid-2025 in Washington, D.C. In just over 10 hours of preliminary test observations, the telescope had already photographed more than 10 million galaxies and stars, and flagged over 2,000 previously unknown asteroids, 7 of them near-Earth objects. The centerpiece was a mosaic of nearly 1,200 exposures, showing part of the southern Virgo cluster, quickly nicknamed the Cosmic Treasure Chest. Spiral galaxies drift across the frame. 3 galaxy mergers appear frozen mid-collision. Faint filament of the cosmic web trace the edges, and deep in the background lies a scattering of extremely distant reddened galaxies. That entire image represents barely 0.5% of what the telescope will eventually capture. Over 10 years, it's expected to record roughly 20 billion galaxies. A second release showed the Trifid and Lagoon nebulae, built from nearly 680 exposures, capturing star-forming regions, open clusters, and a dense globular cluster together in one frame, without losing sharpness anywhere. A single exposure from this camera is so detailed, it will require about 400 UHD television screens to display at full resolution. Within hours, researchers had already spotted a fast-spinning asteroid, later named 2025 MN45, and hints of supermassive black holes in galaxies too young to have grown that large, described by one scientist as like finding a full-grown adult in a kindergarten class. But the telescope's real purpose goes far beyond pretty pictures. Traditional telescopes study one target at a time. This one was built to eliminate the gaps that approach leave behind. Its central mission, the Legacy Survey of Space and Time, will scan the entire visible southern sky every 3 to 4 nights, taking about 1,000 images nightly. The resulting 20 terabytes travel each night via a dedicated fiber link to a processing facility at SLAC, where software calibrates images, corrects for atmospheric distortion, and flags anything that's changed, all before a human ever looks at it. Over 10 years, the survey is expected to catalog roughly 40 billion objects and generate close to 500 petabytes of data, more than every other optical observatory in history combined. What's genuinely new is the element of time. Instead of still photographs, this is closer to a continuous movie of the sky. Every few nights the same patch gets rephotographed, and anything that appears vanishes, brightens, or moves triggers an automated alert to scientists worldwide within about 60 seconds. Supernovae will be caught the moment they ignite, variable stars mid-pulse, asteroids from their first detection, and any interstellar visitor entering on an unusual trajectory will be spotted early enough to actually study. Scientists also expect to find thousands of brown dwarfs, failed stars too small to ignite fusion. According to the NSF, the data gathered in the very first year alone will exceed everything collected by every other optical observatory on Earth combined. The deeper goal, though, is chasing what no instrument has ever directly seen. Fitting its name, the telescope continues Vera Rubin's own hunt. By standard gravity, galaxies should rotate like our solar system, with outer stars moving slower than inner ones. Instead, Rubin and collaborator Kent Ford found outer stars moving just as fast, sometimes faster, proof that unseen mass, dark matter, must be holding galaxies together. Today, scientists estimate dark matter makes up about 27% of the universe, ordinary matter only around 5%, and the remaining 68% is dark energy, a mysterious force accelerating the universe's expansion. Together, dark matter and dark energy account for 95% of everything that exists, and neither has ever been directly detected. By mapping how billions of galaxies are distributed and measuring subtle gravitational lensing distortions, this telescope's data will build the most detailed dark matter map ever made. On dark energy, it will track cosmic expansion through millions of Type Ia supernovae and changes in galaxy cluster structure, aiming to determine whether dark energy stays constant or shifts over time, a question that, if answered, could reshape fundamental physics. Even its brief test run produced striking numbers. 2,104 new asteroids found in just 10 hours, 7 of them near-Earth objects. For comparison, the entire global network of asteroid hunting telescopes finds about 20,000 asteroids per year combined. This one instrument found a tenth of that annual total in a single test night. Over its full 10-year survey, it's expected to discover several million asteroids, including roughly 100,000 near-Earth objects, nearly tripling the current catalog. Earlier detection means longer warning times for any potential impact threat. The telescope's rapid scanning also makes it the most capable instrument ever built for catching interstellar visitors, objects entering from outside the solar system entirely. Only 2 have ever been confirmed. Oumuamua in 2017, whose strange shape and unexplained acceleration remain a mystery, and Borisov in 2019, a more conventional comet-like object. Both were found only after they'd already passed closest approach, leaving weeks to study them. This telescope's faster cadence should catch future visitors much earlier, potentially giving scientists months rather than weeks of observation time. Researchers estimate it could detect dozens over the next decade, each one a physical sample of material from another star system. The telescope's next major task is mapping the skeleton of our own galaxy, something surprisingly hard to do from inside it. Sitting about 26,000 light-years from the galactic center, we're surrounded by hundreds of billions of stars blocking clear views in many directions, while the outer galactic halo is so sparse that finding stars there requires enormous light-gathering power and a wide field of view, exactly what this telescope has. It will rely on Ara Lyrae stars, ancient pulsating variables whose pulse rate directly reveals their true brightness, allowing precise distance measurements across tens of thousands of light-years. In early test images alone, researchers already found 46 of them far out in the halo. By survey's end, scientists expect to catalog around 100,000, revealing that most stars in the outer halo weren't born there, but were dragged in by ancient collisions with smaller dwarf galaxies, leaving behind long tidal streams like the well-known Sagittarius Stream. By mapping these streams precisely, astronomers will reconstruct the Milky Way's entire merger history, a record of ancient cosmic collisions written into positions of stars too faint for earlier instruments to detect. The survey will also catalog roughly 17 billion individual stars across the Milky Way and nearby galaxies, more structural information about our galaxy than has been gathered in all of human history combined. None of this matters, if the data stays locked away. One of the project's quieter achievements is its approach to access. Everything goes public. The observatory's viewing platform is already live, letting anyone zoom from 10 million galaxies down to individual stars in the browser, revealing spiral arms, tidal bridges, and uncatalogued galaxy clusters along the way. Until now, data at this scale existed only inside professional observatory infrastructure. Here it's openly available to anyone. The team has explicitly invited citizen scientists to help, since the nightly data volume will be too large for professionals to examine alone, meaning some genuine discoveries may first be spotted by ordinary people browsing from home. 20 terabytes arrive nightly, and within about 60 seconds of processing, automated alerts go out simultaneously to a small observatory in Chile, a university in Nigeria, a researcher in India, and the largest institutions in the United States alike. No exclusive access windows, no priority queue. The first year's data alone will exceed everything gathered by every other optical telescope in history combined, and the full 500 petabyte archive will likely take generations to fully analyze. The discoveries already sitting in just the first 10 hours of images outnumber what any single research team could examine in a decade. The universe has always been this dense, this chaotic, this alive with motion and collision. This observatory didn't create any of that. It simply gave us, for the first time, an instrument fast enough, wide enough, and deep enough to watch it all unfold at once. Not a snapshot, but a full-length movie of the cosmos. And that movie has only just begun.